As we look at ways where we can deal with integrals that have fractions in them, we're going to look at what we call decomposing a fraction, or kind of pulling it apart. And one method we're going to use is partial fractions. Another method we can use for improper fractions is long division. And so before we jump into what partial fractions can do for us in terms of simplifying integrals, we're going to look at a quick long division problem. So when we're talking about improper fractions, we're talking about the numerator being a larger value than the denominator. So we're talking about, if we're looking at this numerically, we're talking about something like 7 over 4, where this is bigger than 1 whole. And if you remember how you would make this into a mixed number, you would say, well, how many times does 4 go into 7? And 4 goes into 7 once, with a remainder of, after we subtract here, with a remainder of 3. And so we're going to use this concept and look at a fraction involving two functions in the numerator and the denominator. And we're going to call this improper because the numerator is a higher degree polynomial than the denominator. This is a quadratic, this is a linear. So since we have a higher degree polynomial in the numerator, that's defined as improper. And so we're going to use the same technique that we used to use in grade school. And that is, we're going to see how many times the linear expression x plus 2 goes into the quadratic expression x squared. And to write the quadratic expression and get it ready to be divided into, we're going to actually write the full quadratic expression. And what I mean by the full quadratic expression is that really a quadratic expression has 3 terms. It has a quadratic term, a linear term, and a constant term. It's just that the linear and the constant terms have coefficients of 0. So we look at then the leading variable here. We have x to the first power. We need to know how many times x goes into x squared. And x goes into x squared x times. And that's kind of like 4 goes into 7 once without going over. Because when we multiply 4 times 1, we get 4. If we would multiply 4 times 2, we'd get 8, which would be too big. So we're going to multiply x times x to get x squared, and x times 2 to get 2x. So that is x times x plus 2, just the same as the distributive property, and we're going to subtract it. Just like we multiplied 1 times 4 to get 4, and we subtracted it from 7. So we have x squared minus x squared, which is 0. And then we have 0x minus 2x, which is a negative 2x. And then we're going to bring down the 0. And so then we're going to ask ourselves again, how many times does x go into negative 2x? And it goes in negative 2 times. And we can do the multiplication here. Negative 2 times x is negative 2x. Negative 2 times 2 is 4. And then we can go ahead and subtract that. And so we have negative 2 minus a negative 2, which is 0x. 0 minus 4 is a negative 4. And at this point, we have a lower power of x. We have x to the 0 here than we do here. So what we have is x plus 2 goes into x squared, x minus 2 times, with a remainder of 4. Just like 4 goes into 7 one time with a remainder of 3. So we can write then that x squared over x plus 2 really equals x plus 2 plus the remainder, which is negative 4 over x plus 2. Just like we can write this as 7 over 4 really equals 1 plus 3 with a remainder of 7. With a remainder of 4. Or we typically write this as just 1 3/4. So here's an expression that is equivalent to x squared over x plus 2. And that we know how to integrate. So if we put this into the integral instead, then we can integrate this piece by piece. Integral of x is x squared over 2. Integral of 2 is 2x. Integral of this, let's take a look at in a couple of steps, just to remind ourselves what we're dealing with. So I'm going to go ahead and factor out the 4. And we have that when I do that. And so x plus 2 in the denominator, that's kind of like a 1 over x sort of pattern. And so we're looking at that as being the natural log. So we have the natural log of the absolute value of x plus 2. And then doing a chain rule, or I guess a u-sub really would be a more technically correct term for this. We would get a derivative of 1, so just multiply that by 1. And then, since we're done integrating, we'll put in our plus c. And so if you notice, after we start decomposing this original expression into this, these fractional remainders, so to speak, end up being natural logs. And that's going to be a prevalent pattern as we get into partial fractions as well. For this example, we definitely have a proper fraction. We don't have improper like the last example. However, it would be really nice if we just had something like 2 over x minus 2 to integrate, because we know that would be a natural log. We know we'd have to just take the natural log of x minus 2 and integrate it really nicely that way, or 2 over x plus 5. But to have them both as a product, we need to split apart that product. And so as we're looking at this, to split it into 2 fractions so that we have 1 of each in the denominator, it would be kind of like saying we could take, 5 over 8 and split it into something over 4 plus something over 2, and add those 2 things together to get 5 over 8. And so we're going to do that and kind of use that technique over here. So we're going to split this into something over x minus 2 and something else over x plus 5. Now if we think about this, this is a proper fraction. Both of these would be proper fractions. In other words, a would be less than 4 and b would be less than 2. And we could actually have negative numbers up here as well. And so when we talk about being proper and the numerator being smaller than the denominator, in terms of polynomials, since we have linear polynomials in the bottom, we need to have constant terms or just numeric terms in the top, because that would be a smaller degree polynomial than the bottom that would be making these fractions proper. So when we have linear expressions in the bottom, we have constant expressions or just numeric expressions in the top. And we know that this then is going to be numerically equal to the original expression. It has to be, because we want to replace the original expression with these 2 individual expressions. And so what we end up doing then is we end up going through the process of adding these together to make this. And of course, when we add fractions, we need common denominators. For instance, if we need a denominator of 8, then we have to multiply this times 2 and that times 2. And we have to multiply this times 4 and that times 4 to get equivalent fractions. So we end up with 2a over 8 plus 4b over 8. And then we could add them together. And so we're going to do the same process over here. We're going to take this, and to get it to be a common denominator, we're going to have to multiply it by the other denominator. And likewise, we're going to have to multiply this by the other denominator. And so we end up with an expression that looks like a times a times x plus 5 over x minus 2 times x plus 5. And then we end up with this fraction as b times x minus 2 all over same denominator. I'm just going to write it in reverse. Order, x plus 5, which is the original denominator, times x minus 2. And so now that will be mathematically equal to this expression here because we have the same denominators. We can add these numerators together. And so the numerator then starts to look like, when we add these things together, it looks like ax plus 5a plus bx minus 2b all over x plus 5 times x minus 2. And so if we look at this, we have the same denominators. The new expression has the same denominator as the old expression. So if the denominators are equal, the numerators have to be equal. So this whole long expression has to equal 2 in order for these fractions to be equal. So likewise, if we did that over here, that would be like saying adding these together. So we'd have 2a plus 4b all over 8. We're saying 2a plus 4b has to be equal to 5. So this numerator has to be equal to 2. Well, 2 is really 0x plus 2 if we look at polynomial form, and we write it with a polynomial that with the same degree as we see over here. So when we look at this, these coefficients a and b in front of the x have to add up to 0. So a and b need to be opposites so that they can cancel out of this expression, and we're left with just a numeric answer. Likewise, 5a minus 2b have to add up to 2. And so that creates a system of 2 equations and 2 unknowns. So we have the terms that involve the variable x have to add up to 0x. And the numeric terms, 5a minus 2b, have to add up to 2. And so looking at this top expression, that is really just saying a plus b equals 0. And then we have 5a minus 2b equals 2. So we have a system here, 2 equations, 2 unknowns. And however you want to solve that system is up to you. We can graph it, we could substitute, we could eliminate. I'm going to go ahead and do elimination. So I'm going to multiply everything by 2. So I can cancel out the b's. 2 times 0 is still 0, so we're going to leave that as 0. And so I have 7a then equals 2. So a is 2 over 7. And so if a is 2 over 7 and a and b are opposites, that's what this statement says here, that a is the opposite of b, then b must be equal to negative 2 over 7. And so now what I can do is I can put those back into this expression up here. So a over x minus 2, b over x plus 5, I can put in those as numerators. So we have 2/7 over x minus 2 plus a negative 2/7 over x plus 5. And that's mathematically equal to our original expression. So we can go ahead then and integrate that with respect to x. So if we split this into each one of these into its own integral, and we pull out the constant in the numerator, the first integral looks like 2/7 times the integral 1 over x minus 2 dx. This next one looks like minus 2/7 times the integral of 1 over x plus 5 dx. And these, of course, when we integrate expressions now that have just the single term, or the binomial term in the denominator, we know those are natural logs. So we end up with 2/7 times the natural log of the absolute value of x minus 2 minus 2/7 times the natural log of the absolute value of x plus 5 plus c. And now basically we're done with the problem. However, these are really popular multiple choice questions on a AP exam. And they won't give you the answer like this. They will give you the answer using logarithmic properties to kind of condense the answer. So the first thing we'll do is we'll pull out a 2/7. And so you may see the answer expressed like this. But in all likelihood, what you'll see is the answer expressed using the law of logs. Here, when we subtract two logarithmic expressions, it's the same as writing them as a ratio. And so, in all likelihood, you're going to see the expression written in this fashion. So it's as condensed as possible. The process for this last example is identical to the one we just got done doing. It's just that the original problem looks like this, and so we have to recognize that this polynomial in the bottom we can factor into two linear terms and express like that. And so what we really have then is we have a over x plus 2 plus b over x minus 2, and that has to be mathematically equal to 3 over x squared minus 4. And again, we're just putting constant terms in the numerators because we have linear terms in the denominators. We're separating them with a plus sign because, as we saw in the last example, if b ends up being negative, we'll just put the negative up here in the numerator with b. Really, we need to look at this numerator over here from a mathematical standpoint. Instead of looking at it as just 3, we have to really look at it as 0x plus 3. And so we can then set up the expressions as we combine these two fractions as we multiply top and bottom by x minus 2 here, and as we multiply top and bottom by x plus 2 here. So combining these expressions here at the top, we have then we have a times x minus 2 all over x plus 2, x minus 2. And for this next fraction here, we have b times x plus 2 over x minus 2, x plus 2. And that all has to equal 0x plus 3. And I'll just keep the denominators x squared minus 4 over here, knowing that that and this are mathematically equivalent. And so this whole numerator then, when added together, I'm going to add and distribute at the same time. So we have ax minus 2a plus bx plus 2b. And that's got to be equal to the other numerator, 0x plus 3. So again, looking at this, we've got ax plus bx equals 0x, or we can just write that as a plus b equals 0. So in other words, a equals opposite of b. And then we have minus 2a plus 2b equals 3. So minus 2a plus 2b equals 3. So I'm going to go ahead and multiply this by 2. And again, 2 times 0 is 0. So 2a minus 2a is 0. This is 4b equals 3. So b is 3/4. And if a and b are opposites, then a must be negative 3/4. So in this case, that first term is negative. And so if we look at that, then we have, kind of running out of space here, but we have negative 3/4 over x plus 2. And then we have 3/4 over x minus 2. And we are going to integrate that instead of trying to integrate this quadratic term with respect to x. And here's the minus term, the negative term. And that negative term, we know after we do our law of logs, is going to end up in the denominator. So let's kind of keep an eye on this. I'm going to leave it there, but we're going to kind of talk about that. So if I split this into two integrals, we've got 1 over x plus 2 dx, and this one is pulling out the 3/4, 1 over x minus 2 dx. And then we've got minus 3/4 natural log absolute value of x plus 2 here, plus 3/4 natural log absolute value of x minus 2 plus c, and then factoring out the 3/4, and maybe you can even jump to the solution already without the intermediate steps, which is fine. Go ahead and do that if you can. But pulling out that 3/4 gives us this. I just want to make a point here that in looking at this expression, this is the negative expression, this is the positive expression. Our law of logs says we can make a ratio when we have opposites. Okay, and that law of logs says the positive one goes on top and the negative one goes on the bottom. And if you remember the reason why that's the case, it's because if we, and now I'm getting more into logarithms instead of calculus, but if we remember minus ln x plus 2, oops, that's an absolute value, my bad, minus ln absolute value of x plus 2, this is really, the coefficient in front of this expression is really a power. And so this is really ln x plus 2, and again that's supposed to be an absolute value, to the minus 1 power. And we know negative powers means put the expression in the denominator. So that's how this ends up in the denominator. So this is of course a 1 in front of here, which is a positive 1 power, which then stays in the numerator. So that's how we get this, that's how we get the expression there in the denominator and then the x minus 2 in the numerator from a logarithmic standpoint. So I kind of put this up here, which leaves this kind of hanging out here, but that's the rearranging that we're doing, and how important that is to rearrange it to recognize equivalent forms, especially in a multiple choice test, because the equivalent form is usually what shows up here.